Hi, Dr. Anthony Revis here. This is another one of my quick and dirty videos specifically for Saginaw Valley State University Chem 111. And I'm looking at Chapter 3, and I'm going to walk through some slides and give some tips on things to watch out for in doing the calculations. Okay, so taking a look at the slide that says molecular mass, so molecular mass or molar mass. The key thing to remember here is to count all the atoms. And remember, you count from the right side upward, okay? And watch for the parentheses. For example, in this one, where it has sulfur dioxide, there's 1 unit of sulfur and 2 units of oxygen. So don't forget to multiply the 2 times the number of oxygen units. And that is 2 times the molar mass, for oxygen. So you have 2 times 16, and you get whatever that is, 32. And 1 sulfur is 32. So you get approximately 64. Okay, so that's the key thing to look for. Make sure you count all the atoms. Now, when you have parentheses, for example, in the case of magnesium nitrate, the 2 outside the parentheses must be multiplied times everything inside it. Therefore, in the case of magnesium nitrate, you have 2 times the value for nitrogen, and you have 6 times the value for oxygen. So be aware of that. That is a common mistake, that somehow students forget to use the 2 outside, and many students will only use the 2 for the oxygen and forget about the nitrogen. The 2 is for everything inside of that parenthesis, so watch for that. Again, that is a common mistake. Taking a look at lithium carbonate, note that there are 2 units of lithium, and there's only 1 unit of carbon and 3 units of oxygen. The 3 on the oxygen only belongs to the oxygen because there's no parenthesis around it, the carbon. You got it? So there's only 1 carbon. So those are some of the common mistakes, and that's what I'm trying to point out in this video, things to watch for. Not exactly how to do it, but watch out for the mistakes. Otherwise, just add things up. Okay? Now, once you get this molar mass, remember that's gram per mole. So you can use it as a conversion factor. So you can have the grams over the moles, or you can have the moles over the grams. You're always going to have in a gram per mole only 1 mole. So for example, in the case of, let's just take one here, magnesium nitrate, that's 148.3 grams of magnesium nitrate per 1 mole. Do not put another value in front of your moles when you have gram per mole. There's always a 1 in front of the moles. You have a varying number of grams, but always per 1 mole. So you can have gram per mole, or if you need to, you can invert that to mole per gram. What determines, and I'm looking here at the molar mass as a conversion factor slide. So what determines this is how your progression through your dimensional analysis is proceeding. Use your given to drive the ratio or how you set up the ratio. Don't just arbitrarily start by setting up the ratio. I really want to emphasize that. Okay? Use your given to determine whether your ratio is going to be gram per mole or mole per gram. All right? So keep that in mind. And remember, it's always gram per 1 mole. Nothing else. Do not look at the values associated with the formula for it to determine the value that goes in front of the mole. It's always 1. That is, again, it's a common mistake. Students will look at it and say, well, I saw 2 of these units. Yes, but you've already taken that into account. It's per 1 mole always. Gram per 1 mole for a conversion factor. All right, let's see what else can we tell you. When we talk about the molar mass as conversion factor slide, and you have these 9 carbon atoms and all these number of moles and things of that nature, and you'll have, for example, on this slide, we have 1 mole of C9 aspirin, C9H8O4 per 9 moles of carbon. Anytime you have the mole per mole, that is an interconversion factor. It means that you're going from the aspirin to carbon, or you're going from carbon to the aspirin, or aspirin to hydrogen, hydrogen to aspirin. You will use mole to mole when you're going from one species type or one substance to another. That's when the mole per mole comes in handy. Okay, so don't write all these out. Wait until you need it. Typically, that mole per mole kind of happens in the middle of the equations. It almost always does. It's somewhere in the middle of the dimensional analysis sentence, okay, or equation structure. That's where it is. But you use mole per mole when you have, for example, carbon, and you want to relate it to the aspirin or the original substance, okay? So when you do that, you simply look at the substance and look at the number of the atoms of a particular type in that substance. For example, aspirin has 9 carbons. So that's 9 moles carbon per 1 mole of the aspirin. So be aware of that. You only have 1 mole of the substance, right? But you may have 9 moles of carbon, hydrogen, or what have you. So take a look at that. The common mistake made here is, for some reason, students will put 9 moles of carbon and put a 9 mole of the original compound. You only have 1 mole of the original compound. So watch for that when it comes to using these. And this will be an interconversion factor, not just a regular conversion factor, but it will convert the aspirin to carbon or carbon to aspirin. Even if you're looking for grams, you will need this factor to interconvert each time. Converting grams to moles should be straightforward. You'll use grams in the given, and you'll use gram in the denominator in the conversion factor, and mole on the top. And remember, it's always per 1 mole of the substance per grams, or vice versa. And you use simple math to add up the molar mass. That's converting grams to moles slide. Okay. Now, Avogadro's number. For some reason, students like to just all of a sudden, when they get confused, they throw in Avogadro's number. Don't do that to yourself. Okay, and don't start off any of your problems by writing Avogadro's number first. It tends to confuse you. You're going to use Avogadro's number as a conversion factor, and actually somewhat like an interconversion factor. And you will use that when you hear the term atoms, molecules, particles. Okay? Now, don't confuse Avogadro's atoms with atom count. Atom count is a whole number: 1, 2, 3, 4, 5, 6, 7, 8, 9, etc., etc. Avogadro's atoms involves 6.022 times 10 to the 23. And so it's going to be that number of atoms, okay, per mole, that many molecules per 1 mole, that many molecules per that many particles per 1 mole. You got it? So you're going to do this on a per mole basis, but only use Avogadro's number when you hear atoms, molecules, and particles. If it's not talking about atoms, molecules, and particles, do not panic and use that value because you're confused. When you get confused, go back and write your given, stare at your given, then write what you're looking for, stare at it, and then find a dimensional analysis pathway there. But don't just grab things out of the air. It won't work. Okay? All right, so that's Avogadro's number and how to use it. All right, anytime you hear about atoms and molecules and particles, okay, that's when you use it. Now, the empirical formula represents the smallest ratio you can have. It's like factoring in math, okay? So but you have to keep the ratios the same. For example, look at the one where we have C5H10O5, that slide. You have 5, 10, 5, which could be 1, 2, 1, or it could be 10, 20, 10. It has to maintain the same mathematical ratio, okay? And so it's factoring. So think of factoring, okay? And most of this factoring can be done straightforward. It's either 2, 3, 4, 5. You rarely find these problems in Gen Chem, and Chem 111 where it's higher than 5. Typically, they're like 2, 3, 4. So be aware of that. If you're doing some exotic math to determine the empirical formula, you're probably doing it wrong. So just look at it and make the ratios work. Now, the molecular formula tells you the molecular mass or the molar mass. So you use this 5 times carbon, 10 times hydrogen, and 5 times oxygen. That gives you a value, okay? And so that gives you that value. Now, you use empirical molar mass would be 1 carbon, 2 hydrogen, 1 oxygen. So you have 2 different molar mass. One is for the empirical formula, which means that's the smallest smallest ratio of whole numbers you can have, or you have the molecular mass, which has a higher set of values, but those are 2 numbers. If you take the large number and divide it by the empirical number, the smaller number, you will get the number of units. That's the 5, the N value. Okay, so be aware of that. That's the slide on empirical formulas and how to think about them. Let's see, what else can we tell you. Now, let's talk about determining empirical formulas from grams. Okay, it's going to say from grams, and you're going to be tempted to put grams over grams. Catch this. You can not put grams over grams in any of the problems you're going to see in chapter 3. There is no gram to gram ratio. Do not match grams over grams when it comes to empirical formula. So when you see the word empirical formula, you want to get to moles. That is your first goal. Don't think too far down the road. Get to moles first. Once you get to moles, take the large value and divide it by the small value. That's going to give you a whole number. If that whole number is close to 1 or close to 2 or close to a whole number, just call it that whole number. Okay? So then you're going to, so that's going to give you the ratio. The large value over the small one gives you the ratio. So let me say it clearly. You will have a molar ratio of 2 hydrogens per every 1 carbon. That's important to note. Okay, so that's how the math works out. Now, if when you do the arithmetic or do the ratios, it comes out close to 1, you just call it 1, close to 2, you call it 2. But let's say if you get a value of 1.33 or something, you have to use math. I'm going to show you that on the next slides, but I want to be clear. When it comes to determine the empirical formula, you're after moles. And when you get the moles, you want to use the ratio of the large over the small. Okay? Now, take a look at the example where we have Cl. We have a compound is determined to contain 5.31 grams of chlorine and 8.40 grams of oxygen. We're after moles. We have grams, but we want moles. So we converted it to moles using dimensional analysis, and you get the number of moles. All right? And you get a chlorine. Then you get the number of moles of oxygen. When you divide these, you get a ratio of 1 to 3.5. However, we can't use 3.5, so we will double that value, okay, to give you, so you have to multiply everything times 2. So here are the math rules, the way to work out. If you get a value of 1.33 or approximately 1.3, you'll want to triple that, If it's 1.25, you want to multiply times 4. If it's on the halves, you want to simply double those values. That's factoring math that perhaps some of you may have forgotten somewhere. So again, if you do the arithmetic, if you do the division and it comes out to 1.3, just triple everything. If it comes out to 1.25, multiply times 4. If it comes out on the half, 1.5, then you double it. Okay? All right? So be aware of that. All right? So that's a common mistake that happens there. So again, grams, you want to get them to moles. That is the bottom line. Okay? Let's see some other tips that we can give you here. Same thing with all of these slides. Do the empirical formula. You're trying to get to moles. All right? Now, Now, let's take a look at percent composition. Percent composition is parts divided by the whole times 100. So not much to say here. Just remember to use the math. For example, on the 1% composition by formula, you have 2 units of carbon, and you have 6 units of hydrogen and 1 unit of oxygen. You want to make sure you do the math. Don't leave anything out. and you'll get the percent composition. And if it adds up to 100, you're right. If it doesn't, you missed something. That's how you know with the percent composition. So not much else to say about percent composition. Most tend to get that. Let's take a look at the slide that says combustion analysis. And I'm looking at the example where it says carry out a dimensional analysis on both of the two givens. So what you would do if you have carbon and you have hydrogen, or you have whatever species you have, just carry out a dimensional analysis on the given by carrying it through. And in the case of carbon, we have 0.00394 grams of carbon dioxide. We carry it through the dimensional analysis using gram per mole. If we use gram, it's always going to be gram per mole, gram per nothing else except gram per mole. Keep that in mind. Next, you're going to do an interconversion because you want to take it from carbon dioxide, to carbon, and that's important. Likewise, when you do hydrogen, again, it's a slide about combustion analysis. You're going to have water that you're going to transform to hydrogen. So the first thing is grams converted to moles. You can only take gram to mole. Now you have moles, you do an interconversion because you can do mole to mole. And if you look at the molar ratio of hydrogen in water, it's 2 to 1. Okay, that's what you're looking at. Okay, so be aware of that. Common mistake here is making up a new molar ratio or trying to do conversions that frankly don't exist. Molarity is moles per liter. The biggest mistake made here is students tend to overlook converting milliliters to liters. When you do molarity, you must work in liters. If it's given to you in milliliters, you will need to divide that number by 1,000. But you have to show it to me in a dimensional analysis, as we show you on this slide, where we have 355 mils, cross bar 1,000 on the bottom, 1 liter on the top, and we get our molarity. Do not forget your sig figs. That's how we do molarity. Okay, now from molarity, we can get moles. And that's what we show you in this slide, where we call molarity, and then moles per liter. How many grams? So if we think grams, we can think moles. We can get to moles, we can get to grams. In this particular case, we have a molarity of a solution, and we have a volume. But that volume must be in liters, because that's what molarity is in. It is in liters. So keep that in mind when you look at this one. So you have 0.250 liters. Cross hash out the liters. Liters can go to moles because we know molarity is mole per liter. It has to be some chemical ratio that's allowed. Okay, and as you go through your chemistry course, you'll learn some others. So we get moles. Once I get moles, I can convert that to grams by cross hash out the moles and take it to grams. And it's always 1 mole. So many grams per 1 mole. Okay? And that's how you get molarity. Now, dilution is simply going to be looking for one missing variable. That's it. So don't overthink it. Look for a concentration, a volume, a concentration, a volume. Make sure your concentrations are in the same units, your volumes in the same units. Plug and chug. Put it in and punch it through. Do not overthink this. And it doesn't matter what those concentrations are in, as long as they're the same. So you don't have to convert the concentrations as long as they're the same. So you don't care if it's percentage, both a percentage, you're good to go. If both are molarity, you're good to go. If both are some other concentration, you are good to go. Density, looking at the density practice, calculating density, you want to get grams to mils. Okay, and that's it. Find the grams, divide them by the mils, and you got it. Now, if I give you moles, take the moles to grams. Never panic when you get grams or moles. You can always convert them using dimensional analysis, or you can use the molar mass formula, which is gram per mole, which we have in this presentation as well. So I think I've gone through these slides and talked about the important things that you want to know Remember that you can do molar mass by using grams over moles. Don't forget your sig figs when you do this, and don't set up some odd ratio to start your problem. Take your given, write it down. That given will tell you what the very first step is in your dimensional analysis. You can't miss the first step because your given will dictate it. Okay? All right, good luck to you. I hope this helps you a little bit with your prep. And again, it's really a quick and dirty video, not polished. Just wanted to make sure I communicated that to you to try to help you get prepped for Chapter 3 exam, Chem 111, Saginaw Valley State University. All right, that's it.